All right, here's what we got. We're going to start off with implicit differentiation. And remember, when we say implicit differentiation, that's when x's and y's are mixed together, and we have to use the dy dx's. We're taking the derivative with respect to x in this case. A lot of times we're going to do it with respect to t later today because that actually adds a little context to it. But let's take a look at this part right here. We have a couple of things. We've got 1/2 dx dy, or excuse me, 1/2 xy. And I have to take the derivative, and I want to find the derivative. So I want to find dy dx. I have to get dy dx by itself. Well, the first part is I have to do the product rule. And I'm really hoping you can do this in your head now. If not, you're going over to the side here and you're saying, here's u and here's v. Okay? And then you're going to take the derivative of each side. You get dx dx, which, remember, the dx dx reduces out. The derivative of y is dy dx. And then you're going to apply the product rule. But I'm hoping this is the part you can do in your head. So let's go ahead and take the derivative of the first part. We get 1/2 dx dx. So that's the derivative of the first times the original second plus the original first times the derivative of the second, which is just dy dx. And then I have to take the derivative of the right-hand side, which is 0. And then my goal is to find the derivative dy dx. So dx dx reduces out, which means this 1/2 y is going to subtract over to the other side. And then I need to divide by 1/2 x. Now, there's multiple ways you can do this. The reason why I said divide here is notice the 1/2 top and bottom will reduce out. And that leaves me with just dy dx is equal to negative y over x. And there is the change in y over change in x. All right, so that's just the product rule. And then I gave another one, which was just, this is addition, which means I'm just going to take the derivative of each side separately. Sometimes, I didn't do it on the first problem, but sometimes we can write dx dx, because I'm taking the derivative with respect to x of each piece. So I didn't, like I said, I didn't do that here, but I could have. So the derivative of 2x, the 2 is a constant. The derivative of x is dx dx, which technically we don't have to write. The derivative of y is dy dx. And then the derivative of 15 is 0. And the dx dx reduces out, so now I just have to solve for y. Solve for dy dx. So I'm going to minus 2. And then I'm going to divide by 2. That's a weird looking 2 right there. So divide by 2. And I end up with negative 1. All right, so just a quick little review of implicit differentiation. All right, really quick, this is only for juniors. So we've been talking about registration. Hopefully in your first hour, in your third hour class, you got some videos to watch. If not, there's a folder in our Wednesday folder. There's a folder for registration that has everything you need on it. But we are thinking about registering for next school year already. So I just want to give you a quick overview of where we're at and what your options are for next year. All right, so really quick, let me show you this. And again, if you're a current senior, you can tune out for a couple minutes. All right, juniors, you are currently in AB calculus. Your options for next year, and I'm going to kind of do that based off of what you think your interests are for careers or colleges, majors, and minors. All right. So if you are interested in the social sciences, right? So if you're thinking about going into psychology or business or some of those other areas that aren't super math heavy, AP Statistics is probably a really good option for you guys to take in high school. It's a 3 trimester course. Miss Hart and Miss Quebec teach that. Or you could go to BC Calculus. If you want, the nice thing about BC Calculus is it goes fast, but it's going to reteach everything that we've learned in AB. So it'll be a nice review of what we did, which actually will be kind of a pretty relaxing start for about half of the year next year. But it'll really build your skills from this year. It's fast paced, but it is for anybody who's interested in a science major or a medical major. If you're going to the medical field, anything like that, BC Calculus would be highly recommended. Um, and it is it's a full year of college math. So considered to be Calc 1 and Calc 2 of a regular university schedule, which is 2 semesters worth. We are currently in AB, which we spend all year learning a semester worth of calculus. So you can kind of see how fast BC goes. If, and this actually would not be an option, you can't take multivariable until you get BC. So for us, multivariable calculus is not an option. Okay. You could do computer sciences. So this is a 3 trimester course right here. And you could also do, sorry. So by the way, that's a 3 trimester course, 3 trimester course. This one is a 3 trimester course. APCS, Computer Science Principles, is a 2 semester course. So I believe that starts first and second trimester. If you don't want to fully commit to stats, calculus, or a 3 or 2 semester course, we have 1 trimester electives. So we have computer programming 1. This is, again, it's 1 trimester. Or we have prob and stats, which is also a 1 trimester course. One of the dangers with these two is we need a certain amount of students to sign up for it. So just because you signed up for it, if we don't get enough students, then they might not be offered. But those are nice electives that you could take. So here's your options for next year. None of them are required because you've already met the requirements for high school graduation, but think of the university you want to go to. Some of them require 4 years of high school math. And what that means is every year you're in high school, you're taking some form of math, whether that is calculus, stats, BC calculus, or computer science. So there's where we're at. My advice for you is if you feel like you do want to go into the medical field or math major, minor, anything with the sciences, BC calculus will probably be your best bet. If you're thinking you're a business major or communications, anything else like that that isn't super math heavy, then I would say AP Stats. If you really are focused on computers, then the computer sciences is your way to go. So if you'd like to take a screenshot of this right now, if it helps, go ahead and please do so. We have a pretty heavy day, but I will be available in my office hours from 1 to 2 today that you could stop in and we could discuss any questions you have on how to register or what to register for math. Okay. If you have
But
questions, go ahead.
I was just gonna say that isn't AP Calculus BC just everything that we learned in AB?
No, yes and no. So AB is is part of BC, so it's a subset of BC, which means if you took BC, you are going to relearn almost everything that we've learned this year, except it's going to go faster, and then you're going to build upon it to get the second trimester, semester worth of college calculus credit. So, okay, so we are going to shift gears a little bit and start talking about related rates. I have a handful of slides that I don't want you to write down. This is kind of just building the conceptual side of what we're doing today. So I want you to think about this. Think about what happens when you blow up a balloon. Right? Well, what's changing? As you inflate the balloon, there's a lot of different things that are changing, and here are just some things to think about. Things that are changing: the diameter, the radius, the surface area, the size or volume of the balloon, the height, the width, right? However you calculated those measurements, but the mass is changing, right? The density, there's pressure, there's time, all of these things are changing. And the question is can you change just one of these without affecting all the other ones? The answer is no, right? The balloon is going to take the shape that it's going to take as you blow it up. But as you're blowing that up, the change in one item will affect the change in the others. And the rate at which that balloon is changing, maybe it's the rate the radius is changing, that rate is affecting the rate at which the surface area, the volume, the pressure, everything's kind of based off of time. All of that is related. And that's the idea of what we're doing today is we're going to start learning something called related rates. So today's topic, this should be, we have a new textbook. This should be 4.3 day one if you're looking through your textbook at all. Go ahead and write this down really quick. 4.3 day one, related rates. Right? Well, problems where multiple quantities, which when we say multiple quantities, we're really referring to the variables, have a relationship between them, and the change in one variable affects the change or the cause in the change of the others. And we're going to explore a lot of different types of problems. So the question here is, we keep talking about this idea of change, right? Change, the change. How do we represent change in calculus? Well, change has always been the derivative. Now, it could be dx dt. Now, we're going to change with respect to time, and that's everything we're going to look at has the change with respect to time. So I could change dy dx or dx dt. The next slide I got basically a slide that kind of breaks down how does it look if we have dx dt. What does that mean? You'll see that in just a second. Okay, so the big thing is we represent change using the derivative. And there are multiple things that can change at the same time, which means we need to use implicit differentiation. So anything that has a variable, we're going to be taking the derivative of it with respect to time. All right, I don't want you to write this slide unless you really want to. This is just kind of the same thing. So all variables are differentiated with respect to time, not just x. All right, so here's a quick example. Let's say I have dx dt. What does that mean? Well, this is the change in x over the change in t, and x is going to represent something in our problem, and t is going to represent time. So if I have dx dt, it's how x changes with respect to time. Same thing with dy dt. How does y change with respect to time? Or sometimes it can be theta. Theta is just an angle measure. So it's how an angle measure changes with respect to time. Or dh dt would be how the height changes with respect to time. So all of those are, notice it's all dt. And you'll get this as we go along. Big thing here, Important note, when solving related rate problems, only substitute in the given values into an equation before taking the derivative if those numbers are not changing. You don't need to write that because we'll show you that as we go through these things. Okay, now here's what I want you to do. I just need you to experience a couple of these problems without writing them down. These notes will be posted written out on my on our Schoology page, and I'm doing a video of this that you can always go back and watch it if you need to. But we're going to do a handful of problems today. I just want you to see what it looks like a couple of times without writing it down. All right. So I will ask you to do this. Put your cell phones away. Right. I don't know if you have them out, but if you do, put them away. And let's just focus on what's going on. And I'll show you, this is our very first related rates problem. All right. So you can see there are a lot of word problems today. And one of the things you can do is read them carefully and just kind of identify what you know. My advice is read the problem all the way first, all the way through. So a rectangle has a length of 11 inches and a width of 4 inches whose sides are changing. The length is decreasing by 3 inches per second and the width is shrinking, or I could have said decreasing as well, at a rate of 5 inches per second. What is the rate of change of the area? All right, so the first thing you're going to do is read it, and then you're going to draw a picture. So I have a rectangle, and we know the length is 11 inches. We know the width is 4 inches. And then we know a couple of other things, and this is the part where it's kind of interesting. The length is decreasing by a rate. So right there, the length is changing. That's going to tell me that dl dt, everything is with respect to time. In this case, time is seconds. And notice it's decreasing. So that actually is going to tell me that it's negative 3 inches per second. So that's my rate that the length is changing. And then it says the width is shrinking at a rate. So if the width is changing, that's dw dt. And it's shrinking, so it's negative 5 inches per second. If it was increasing, it would be a positive, but you have to really read carefully to identify those words that represent if it's growing or shrinking. All right, now, what are they asking us to find? And that's the other important part. At what rate is the area changing? So I want the rate of the area with respect to time. All right, so here's what I like to do. I like to fit these things in my problem. So if I know the length, and I know the length is changing at negative 3 inches per second, and then I know the width, and I know the rate at which the width is changing, okay? But then I also know one other thing. I know that area is equal to length times width. And that's where the equation comes from. And that's sometimes the hard thing to do is they didn't give me this equation. I had to know that it's a rectangle and the area of a rectangle is length times width. So here's what I'm going to do. I have my equation, right? But that equation doesn't have anything with rates in it. So I need to do implicit differentiation, which introduces the rates. Now, notice if I take the derivative of both sides, this is what I could have showed on the warm-up is I'm going to take the derivative with respect to time. So we're going to implicit differentiate take the derivative with respect to time. Right? That's the dt. So watch what happens. The derivative of a, capital A, is just a variable. That's dA dt. Okay, so when I write that in my brain, I'm thinking that's the rate at which the area is changing with respect to time. And then notice right here, what do we have? We have a product rule, Right? So I have to take the derivative of the first, which is dl dt, times the second, which is just w, plus the first times the derivative of the second. And the derivative of w is just dw dt. Now notice how I didn't plug any of these items in, and that's one of the things. You want to always do implicit differentiation first, and then you can plug in the information that you know. So now we're just going to plug in what we know. Well, I know the rate at which the length is changing. They told me that right here. That was -3. I know the original width is 4. I know the length is 11. And then I know the rate at which the width is changing. That's -5. And the only thing that's left over, the only thing I don't know, is the rate at which the area is changing. Well, now it's just algebra. So here we get, this will be -12 and -55. When I add those together, I get -67. And then a lot of times on a question like this, they're going to actually ask for the correct units. So you have to interpret, well, wait a minute, what did I do? I have the change in the area, and everything is measured in inches. So area would be inches squared per time. Well, time is in seconds. And there's the rate at which the area is changing. So once you get the hang of this and you see it a handful of times, it becomes much friendlier. But I will admit, some of these problems are just plain hard. All right, and we'll get to them as we go. So, quick overview, what did we do? We read the problem, we identified the rates that we knew, we identified the rate we want to find, and then we drew a picture to just help us visualize what we have and what we know. And then we had to also find the equation that we needed to take the implicit differentiation of. And that specific was the area. So then we took the derivative with respect to time. We got that's where the rates appear. And then it's all algebra. You plug in what you know and you solve for what's left. All right, let's try one more. I'm going to go through this one a little faster without kind of showing all the work and writing all the steps out. But let's take a look at what we have. So first, I'm just going to read the problem all the way through. A pebble is dropped into a small, still pond, and it makes a ripple that extends or expands with the radius changing at a rate of 3 centimeters per second. How fast is the area of the ripple changing when the radius is 15? So I'm going to draw a picture here. And we have my radius, and that's about it, right? Then we have area. So how fast is the area changing? Well, what do I know? I know the area is pi r squared, right? That's the area of a circle. And some people like to do this first. They actually just like to write the equation, and then notice I don't have any rates in this equation until I take the derivative of it. And we're always going to take the derivative with respect to time. All right, so let's see what happens here. Take the derivative of a, that's dA dt. And then pi is a constant. R squared, I can take the derivative of this just using the power rule. The 2 is going to come down, so I get 2 times pi times r, technically r to the first power. But then I took the derivative of r, so we are doing like a chain rule here, where I have dr dt. Notice how I didn't plug any of the numbers in yet. I took the area equation, I took the derivative introduces the rates. Now I'm going to look at what I know. How fast, that indicates a rate, right? How fast is the area changing? So they're asking me to find dA dt. So I don't know what dA dt is. That's what I need to find. But what else do I know? I know that how fast is it changing when the radius is 15 centimeters. All right, so I'm going to plug in 15 for r. The radius is 15. But then I have to know how fast the radius is changing, dr dt. Well, it says right here that the ripple expands. So that expands means it's increasing, and the radius is changing at a rate of 3 centimeters per second. So the radius is changing at positive 3 centimeters per second. So that's the part. dr dt is 3, the radius is 15. And then if I want to keep this as an exact answer, I know 2 times 15 is 30. 30 times 3 is 90 pi. That's a better answer than any decimal we can get. But then I have to think of my units. Area, change in the area. Well, the radius was 15 centimeters. So area is squared with respect to time. And I just want to double check. Notice it's in seconds. So it's centimeters squared per second. Centimeters squared represents the area. The seconds represents the time. Okay. All right. Now, I will admit, once you get the hang of it, these two are the easier problems you're going to see. There was nothing really tricky with these two problems. It does get harder, and that's what we're going to do right here. So, I am going to have you write this down in just a second, but I want to paint the picture first before we get into this. So this is like a classic related rates problem. It's called the falling ladder. And I've seen this question on an AP test before. So I just want to make sure that you guys are clear that this is really important. Okay, so let's look at this. A ladder is 17 feet long and it's leaning against a house. But the ladder is sliding along the bottom at a constant rate of 2 feet per second. Let me show you a quick visualization of what this is basically doing, just so you can see it. This isn't exactly the problem, but this is what's happening. Notice, the ladder is sliding down. If I stop it here, okay, the ladder is sliding at the bottom at a specific rate. And as time increases, what happens? The ladder gets further away from the bottom. And then eventually, there's going to be a time at which the ladder is completely on the ground. Now, there are other factors involved here that we kind of don't take in play. We're going to assume the ladder is sliding at a consistent rate. All right, so that's one thing we need to look at. But I just want you to get a visual. This is what's happening. The ladder is falling down. Okay, so I would like you to basically write this part right here, just this part right here. And one of the benefits, you don't get any credit for drawing pictures, but it helps. It really helps. So we're going to use this problem to really answer a lot of questions. And I need to do this first. So go ahead and write this down. Just write part A. Oh, sorry. I thought this was copied a little bit differently. And we really have 4 problems in one, but we're going to do them one at a time. All right. So 17-foot ladder is leaning against the house. We have the rate at which it's falling away at the bottom. And then the question is, how fast is the top of the ladder sliding down the side of the house when the base is exactly 8 feet away from the house? So we're going to draw a picture first. And I'm not saying that this Picture has to be anything great. There's my ladder. It's up against the house. We know a couple of things. I know the ladder is 17 feet long. How fast is the top of the ladder sliding down when the base is 8 feet away from the house? So we know that this distance on the bottom is 8 feet. Now you might be thinking, well, wait a minute, they don't tell me anything about area. So what equation are we going to be using? That's really one of the harder things to do with this problem. So the question is, what equation deals with the lengths of a right triangle? And that is where I'm just going to kind of write it out. A, B, and C. That's our Pythagorean theorem. So we always wrote C squared equals A squared plus B squared. And they are assuming that you know when you're given lengths of a triangle and rates, you're going to apply the Pythagorean theorem. There isn't any part in here that told me I have to use the Pythagorean theorem, but we had to pull that out of our experience from just previous years. All right, so let me make this look like a B. So what do we know? Well, I know that the ladder is 17 feet long. And I know that we want to figure out how fast the ladder is sliding down when the base is 8 feet long. So those are the two things that they give us. And what I want to do is I don't want to get too crazy with this because a lot of times kids start plugging things in. So how about we just start with the fact that I'm dealing with lengths of a right triangle, which is the Pythagorean theorem. Right? Now, the rates do not appear right here. So I need to do implicit differentiation to find the rates, and that's where rates will appear. So I'm going to take the Pythagorean theorem, and I'm going to take the derivative with respect to time, and that's what gives us the feet per second. That's what will give us our rates. All right, so when I take the derivative of c squared, I get 2c, but then we kind of think of the chain rule, right? The derivative of c is dc dt. And then I have to take the derivative of a squared. So the 2 comes down. I'm left with a to the first power. But then we've got the derivative of a is dA dt. And then it's the same thing with b. The 2 comes down. And we're going to multiply by the derivative of dB dt. So look at that. When you take the derivative, we have 3 rates, a rate for each variable. And you should know, kind of just by the variable alone, dc dt is the rate at which the ladder is changing. dA dt is the rate at which the ladder is falling down the house. And dB dt, because of the way I labeled it, is the rate at which the ladder is moving away. Now, some of these we know, some of them we have to interpret and find out. But notice the big thing. We took the derivative, so we did implicit differentiation to find the rates with respect to time. And then the next thing we're going to do is we're going to plug in what we know. But this is tricky. So Let's take a look at just what information they told us. So the ladder is leaning against the house. It is sliding away from the bottom at a constant rate of 2 feet per second. So I know that this rate is going away. Now notice, that's the rate that's B is changing with respect to time. This length is getting longer, so this is going to be a positive 2 feet per second. Okay? If we were going closer to here, then the distance was shrinking, then it would be negative. But they don't tell us that. We have to interpret it. So I know dB dt is 2 feet per second. I want to find how fast is the top of the ladder sliding down the house. So what they're asking us for is find dA dt. So that's what I need to discover. Now I will say this, if the ladder is going down, what do you know about your rate? Right? You should know your answer already is getting smaller, which means this rate should be decreasing. So I should know that this answer should be negative. But I'm just going to leave dA dt as is. And here's the tricky spot. dC dt, right? The rate at which the ladder is changing. Wait a minute. How long is the ladder? 17 feet. If the ladder is sliding down, is the length of the ladder ever changing? No, it's constant. The length will always be 17 feet no matter how much this slides. So you have to know. You have to read into this and say, since the ladder isn't changing, its rate is 0. And that's the tricky spot. A lot of kids end up forgetting about that. All right, now let's plug in the other pieces that we need. So I need to figure out what are the other pieces. So I have 2 times C. Well, what is C? C is the length of the ladder. But since the rate is 0, none of this will matter. A, well, wait a minute. A is the height of the ladder when the bottom is 8 feet away. Well, this is a quick Pythagorean theorem problem. You don't need to show any work for this. But if I want to find the length of A, we've got 17 squared, which, by the way, I believe this is a triple. If you remember the triples, then you don't need to show any work here. And I'm going to do this in my calculator. I'm going to take 17 squared, I'm going to subtract 64, and then do the square root. And you should get 15, I believe. I'm going to double check that. Yeah. So notice, we had to find that. They didn't tell me it. They're going to tell you the least amount of information, the minimum amount of information. You just have to find the rest. So we know that A is 15. And then B, they did tell us 8 because we're going to figure out how fast is the ladder sliding when the base is 8 feet away. So look at that. We know everything except dA dt, and now it's just algebra. Okay. The nice thing is 2 times 17 times 0 is still 0. I get 30 dA dt plus 32. And then I'm just going to go ahead and subtract 32. At the same time, I'm going to divide by 30. And there's my rate, but we can reduce this. And I'm going to leave a little bit of a space because we should think of the units. dA dt, Notice the answer is negative, which is what we thought, right? Well, what is it? It's going down. And what is the length on these units? This is feet, feet. So A is 15 feet, which means it's changing at a rate of negative 16/15 feet per second. Which, if I plug that into my calculator, depending on what they asked for, if they asked for the exact answer, you would want to leave it as negative 16/15. Or if they said round, or they might not even say round, if they didn't ask for a way to write your answer, you would need to take it to at least 3 decimals and then provide the correct units. So notice why this isn't feet squared, because we're not finding the area. We were only looking at dAdt, which is the rate at which the ladder is sliding down the house. And hopefully the answer being negative makes sense. All right, so that's the first part. Now I will say that now that we found this rate, we can use this answer. We know dAdt, so we can use it to help us answer anything else in this problem. And let's find option B here. I'm just going to keep sliding these down. Okay. So we're going to use the same idea, the same concept that we have here. Now, what is the rate of change of the area of the triangle at the same time? Let's think about what we know. So at the same time refers to all of this information that we just discovered is accurate and true. But what they're looking for, what is the rate of the area? Okay, so they're asking me, what is, and I use a capital A here, dt. I want to find the change in the area with the change of time. Well, that tells me I need to use the area of a triangle. And since I used A, B, and C already, let's use those same variables just to write our equation. So area is 1/2 the base times the height. I called the base of this triangle B, and I called the height of it A. So there's my equation. Right? In my mind, that's one of the hardest things to do about problems like this is just to figure out what equation do you need to use. And don't be confused. When I use lowercase a, that's referring to the side length. When I use capital A, that's referring to the area. All right, so there's our equation. Now we have to take the derivative with respect to time for both sides. And you'll notice there is a product rule here. So I want to just make sure that we can do this in our head without showing all of that work. So we're going to do the product rule, but let's take the derivative of the left side first. So the derivative of the area with respect to time, the derivative of the area is just dAdt. Now I've got the product rule. I'm going to do 1/2 the derivative of the first, which is just dB dt, times the original second plus the original first, which is just 1/2 b, times the derivative of the second. Right, so there's my product rule. Notice how we're using those rules to help discover new things. That's what calculus is all about. Use your skills that you've learned before. Well, now this is actually really friendly because from the previous question, our answer for dA dt is negative 16/15. And they told us the rate at which B was changing, that was 2 feet per second right here. So that was given as well. We found what A was. A was 15 feet. We found what B was. B is 8 feet. We know everything. So we're just plugging in the information we know now. So we wrote the equation. We took the derivative to find the rates. And now we're just going to plug in what we know. I'm going to space this out a little bit. So we know that A was 15. I know B was 8 feet. That's the base and technically the height. And we knew from the start of the problem that the base was changing at positive 2 feet per second. That's dB dt. And then our answer from part A was the rate at which A was changing was negative 16/15. And here's where you want to take the fraction, because we technically shouldn't use this answer if it's rounded. The only time you round your answer is when it's your final answer. So that's why I'm going to recommend using the negative 15 or negative 16/15. Now, the nice thing about this is we could do some quick algebra here. Let me do this quick. And we can just reduce some things. 1/2 and 2, well, those are going to go away. So I'm left with 15 plus 1/2 of 8 is 4. And you could do 4 times 16. And at this point, I'm going to use my calculator, but you could change this to a denominator of 15 and all that. But I'm not going to spend time doing that right now. So I'm going to do 15 plus 4 times negative 16/15. I turn it back into a fraction. We get 161 over 15, which is roughly equal to 10.733 repeating. And then we should think of our units, right? dA dt, this is area, and everything was in feet, right? So if everything was in feet, this would be the area is feet squared per second. So you always want to think of dA dt. What is the units for the area? It's feet squared. T in this case is always time. And time was always in seconds. All right, so notice the process. We discovered what equation we needed. We took the derivative to find the rates, and then we plugged in everything we knew and we solved for whatever was left over. That's basically the process we're going to do. Okay? All right, part C could be challenging. It's just tricky. We got to be careful. I'm going to redraw the picture for this one just to kind of help us out here. So I'll give you a second to write part C down. What is the rate of change of the angle between the ladder and the ground at that exact same time that everything was happening before? So a new picture could really help us out here. Think about what we know. And again, this picture doesn't have to be perfect, but we know it's a right angle. It's always assumed, by the way, that if you have anything going up and down, that it's at a 90-degree angle, because that's what forms right triangles, and we need that. So what do we know? We know that the ladder was 17 feet. That was given in the very first problem. We know that the ladder was 8 feet away. We also know that the ladder was changing at a positive 2 feet per second. And we do know that dc dt was 0 feet per second, right? Because the ladder's not changing. But now they're not talking about anything with this side length. What they're talking about is they're saying at what rate is the angle changing between the ladder and the ground. So wait a minute, they're saying this is our angle theta, which right away, hopefully you're seeing, ooh, wait a minute, I've got a right triangle where the hypotenuse is 17. The side that's connected to it is the adjacent side. So I have adjacent and I have hypotenuse, and I'm hopefully you're thinking this is just a SOHCAHTOA problem. So the question is then which SOHCAHTOA involves adjacent and hypotenuse, and it's cosine. So that's the problem that we need to set up, is how do I get the equation? It's not lengths, it's not area, it's dealing with an angle. And it's saying that the cosine of some angle measure theta is equal to the ratio of the adjacent side over the hypotenuse side. I want that to be C. Now notice, I didn't plug anything in yet. I didn't plug any numbers in. I just set up the equation. So I'm going to give you a second to get caught up and let me know. So all this picture, all this information was what we had from before. The only new part is we're looking at theta. And that theta helped me think of SOHCAHTOA. And cosine is the ratio of the adjacent over the hypotenuse. So that's what sets up this equation. So if this is the equation, I now want to do implicit differentiation, but there's a little bit of a trick. So if I take the derivative of both sides, it's pretty friendly over here, but it's not super friendly right here because that involves a quotient rule. Now you can totally do this. If you want, you can take the derivative of the left side and the right side, or if you want to take, instead of having this divide by c, here's where we got to be really careful. We can move this c over to the other side so it looks like this. And in my mind, this is easier to take the derivative of because it's the product rule instead of a quotient rule. But again, it doesn't matter. I just think by doing the quotient rule, that makes it more confusing. But it completely won't matter. All right, so let's take a look here. I want the derivative of both sides. Well, I'm going to take the derivative of this part. Now, this is a product rule. So the derivative of this c is dc dt. And then we're going to keep the original cosine of theta plus the original first times, now we're going to do the derivative, I'll do that in green, Now I have to take the derivative of cosine. Well, the derivative of cosine is negative sine theta, and you could put that negative right out here. Make that look more like a theta. But then we have the chain rule, right? Theta's on the inside, so I have to take the derivative of theta, which is d theta dt. That's the rate at which the angle is changing, which is what we want to find, right? The rate at which the angle is changing. So I want to find d theta dt. And then that's going to equal the derivative of the right side. And the derivative of the right side is friendly. That's just dB dt. So notice, I didn't plug anything in yet. But now I'm going to take a look and see, well, what do I know? Right? I know dc dt is 0, which is really friendly because that gets rid of this part. I know what the c value is. The c value is 17. I know what dB dt is. That's 2. The only thing that's missing, I want to find d theta dt, right? I want to find the rate at which the angle is changing. So I want to find d theta dt, but I don't know what theta is. Now you have a couple of options. You technically don't need to know that, right? You could do it, but isn't cosine of theta just equal to the ratio of the adjacent over the hypotenuse? So isn't cosine of theta really just 8 over 17? And then the sine, isn't sine just the opposite over the hypotenuse? Well, we do need to know this opposite then if we're going to do that, because the opposite side we found in the earlier problem as 15. So this ratio is 15 over 17. Okay, so let's look at what we know. One of the friendly things is dc dt, that's 0. Which means I really didn't even need to know what cosine of theta is, because 0 times that will go away. I know what c is. C is 17 feet. I don't know what d theta dt is. That's what I have to find. And then I know what dB dt is. That was equal to 2. Well, even friendlier, look at what happens here. This turns into 0, right? So that goes away. 17 on top and 17 on bottom, that goes away. So I technically have 15 over 1, or 15 d theta dt is equal to 2. And then if I divide this over, oh, I did forget the negative, sorry. That should be a negative. I'll share with you why I caught that when I did. But this is a negative 15/17, which means this will be a negative 15. And then if I divide by a negative 15, I end up with my change in angle measure. So the angles are always in radians, and then over the time was in seconds. Okay, and then 2/15 can't be reduced, so that's my answer. Radians per second. Now, why did I know that I forgot a negative? Well, if this is falling down, if the ladder is falling down, your angle is actually changing. It's getting smaller, right? As the ladder gets closer to ground, this theta is getting smaller, which means its rate should be negative. And that's what made me think of when I was thinking of dividing this over, I thought I was going to get a positive 2/15, which means the angle would be growing. So I thought, oh, shoot, did I screw up? And I did because I forgot that negative right there. But thankfully, I caught that. And it was because I'm thinking about my answer and how it relates to the change in the angle that made me realize that there should have been a negative, and that was the spot at which I had forgot. So I'm actually kind of thankful that that happened. Okay, this is a lot. I understand, and you're probably kind of freaking out right now. We're going to spend a full week on this, so you'll get some time to process it. All right, let's end on a more friendly one really quick. Same problem, same everything. What is the rate of change of the perimeter of the triangle at the same time? And again, I'll post these notes, so if you missed something, you can always go back and get it. All right, what is the rate of change of the perimeter? Well, here they tell me what equation to use. You don't have to redraw this triangle because you guys already have it, but I'm just going to draw what we know. We knew A was 15, we knew B was 8, we knew C was 17 feet, and then we knew their rates as well. I always put the units in there so I don't forget. And then dAdt, I have to go back and steal the answer from part A. That was negative 16/15. So notice how we're using our answer in part A to help us out. Feet per second. Okay, now notice perimeter means the distance around the shape. So I'm going to set my equation up as, well, what is the perimeter? Perimeter is the distance of A plus B plus C. And what is the rate at which the perimeter is changing? Right? When I read this, what is the rate that the perimeter is changing? I'm looking for dP dt. So here's my equation for perimeter. Notice I didn't plug anything in yet. We don't want to do that until we take the derivative of it. So I'm going to take the derivative of each piece. So the derivative of P is just dP dt. The derivative of A is just dA dt. The derivative of B, dP dt, and the derivative of C is dC dt. Now it looks scary, right? But we know all three of those rates already. They're already given. Part A, we found the rate of dA dt. dB dt was given. And dC dt, that's the one that we had to infer, right? The latter is not, it's 17 feet for the entire trip. So the rate at which the ladder is changing, the ladder never changes, so its rate is 0. So let's plug in what we know. And you could rewrite this as 30 over 15, right? Because 2 is the same as 30 over 15. And then you could add those together. And you would get negative 16 plus 30 is 14 over 15. And then what are the units? Right? My units are the perimeter. Now, perimeter is always just regular units per time. And what is time? Seconds. I will admit, we basically did 4 problems here. Don't think of this as just this is what every problem is going to look like. We really did 4 separate problems. I want to go up here and really quick and check. Okay. All right. Now, I wasn't sure how long we were going to have with all this, so I have a lot more examples. We're not going to go through them all. Um, and my computer just froze up too. Let's see. Okay. If you would like to take a screenshot of this, you can. I didn't give you these steps right away because I don't want you to just solely focus on here's how you do it. This works every time. But this is basically the steps to solve a related rates problem. Read the problem, draw a picture, use the variables to represent the quantities. So we used A, B, and C. We saw other ones where it was length and width. Then we have write the equation that relates the variables together. That's the hardest part. What equation do you use? And then we differentiate with respect to time, right? We are always going to, I might change that to time if my computer's freezing up. I can't. This should be time because we don't do anything other than time. And then once you take the derivative, that's when your rates appear. Once the rates appear, then you can fill in everything you know, and it's algebra from there on out. All right. Um, so if you wanted to write this down, you can come back and grab it. It's in the notes. We don't have a ton of time left. I want to just get through a couple other things. Let me just show you this problem quick. I don't want you to write it down, and we might not even be able to do it. But somebody's inflating a balloon. Now, here's the nice thing about this problem is we would give you the volume of the balloon. All right, so write an equation that relates the change in the volume to the change in the radius. Well, what we would need to do is we need to assume the balloon is spherical. Right? And we're not going to include the little tab here that you use to blow up the balloon, but what is the volume of a balloon? The volume for any sphere is 4/3 pi r cubed. And then there's my equation, so I would take the derivative of both sides. The 3 comes down and turns this into 4 pi r squared times dr dt. And here's the equation. Sometimes that's all they want is write the equation. And then other times it says the balloon is being inflated at a rate. Notice, without even looking at this rate is volume. So they tell me in this problem dv dt is equal to 10 pi. How do I know it's volume? Because the units say it's cubed. So I would plug 10 pi in here, and then that equals to 4 pi r squared dr dt. And they want us to figure out how fast is the radius changing when the radius is 4. So I would plug 4 into the radius, and then you would just solve for dr dt. So I wanted to show you that one quick. And then the other thing is I have a couple of problems. I'm going to put these up here, and these are right from Delta Math. So if you go through the homework tonight, you're kind of stuck. Go back to this part, and I just have all the worked out solutions written in here for each type of problem you're going to see. All right. I will admit you have 2 problems on tonight's homework that are a little more challenging. You might have to watch the video on that one, and we're going to come back on Thursday, Friday, and go over this problem right here. So this is like the last part of our Delta Math homework. I think there's 2 questions where I'll just show you quick. They give you the area formula, and they give you everything about the area. Then you have to use that to find the missing value, but then it relates to circumference. So then you have to use the circumference piece to find the missing part. So that might be a challenge. We will definitely go over that. And this is what we got for homework tonight. So your homework tonight is 4.3 day one related rates. It's in Delta Math. Submit a screenshot of your end slide when you're done, so it just shows that you did everything. And then just a reminder for Wednesday, juniors, you have to register. So part of Wednesday is you guys registering for next year's classes. But everybody is going to be asked to watch the Ed Puzzle video. Um, so I will reach out. Serena, I know you just joined us, so I'm going to send you an email with directions how to sign up for Delta Math and how to sign up for Ed Puzzle and how to sign up for AD Classroom. So, Serena, I'll get you everything you need. If you have any questions, stop on into my office hours. I will be available 1 to 2 o'clock. Um, there's a link on our Schoology page. Join us, and I can help you through anything you need. All right, that was a lot. Have a good day. Welcome back.